Hello guys, welcome to today's video. Today we're going to discuss some properties of compact operators, and I would like to jump straight into the first remark, which is let x and y be norm spaces. The set kxy of all compact linear operators from x to y is a subspace of Lxy. Well, the way we prove it is that in order to prove that kxy is a subspace, I just need to show that the laws of vector addition and scalar multiplication holds true. So what I mean by that is, if I take a compact operator T1 and I take a compact operator T2, then T1 plus T2 should also give me a compact operator. Similarly, if I have a compact operator T, then alpha times T should also be a compact operator. So let's start with this. So if I have T as a compact operator, then I know that it is compact if it maps a bounded subset of X to a relatively compact subset of Y. So in the theorem above, or in the lemma above, we saw a statement that M is relatively compact as a set. Okay, M is relatively compact if and only if M is totally bounded. And what do I mean by totally bounded? I just mean that for every epsilon greater than 0, I can find points x1 to xn such that X is contained in the union of all such balls with radius epsilon centered at those points x1 to xn. So if this holds true, then I say that okay, T is compact as an operator, or if T is compact as an operator, then this holds. So I know that T1 B10 is relatively compact because T is compact as an operator, T1 is compact as an operator, and it maps bounded subset in X to a relatively compact subset in Y, which means if it is relatively compact, then it's totally bounded, therefore this condition holds true. Now similarly for T2, this condition holds true. And now it all boils down to your knowledge of analysis. Now the function analytic part is over, now analysis. Now what happens is, we have two balls, or the union of different balls, and now what I want is, if I add these two together, so what would I get? So when I add these two together, the resultant, if I can find that the resultant is also contained in some ball of some radius, or the union of some balls with radius epsilon I to say epsilon n, or and the center point, then if I can prove that this plus this can also be contained within a ball, or within a union of all such balls, then I can prove that T1 plus T2 is also compact as an operator. And the way I do is, I draw a ball centered around X with radius R. And then I have another ball centered around Y with radius S. And now I add just these two balls. So when I add these two balls, I can say that this is a subset of this set. Of course, try to think of it this way. So if I have this ball and if I have this ball, so by ball I just mean a collection of all points. Now if I add each point in here to each point in there, what would I get? What I would get would not be greater than something like this, you see. So that's what I'm trying to say. What I want to say is that if we have two balls and if we add them, then they would be contained within a bigger ball centered around X plus Y with radius R plus S. Now do it for all combinations. Why I say this combination word is because now we are not just adding two balls here, we are adding two sets which consist of union of many balls. So when you would be adding these here and here together, let me write a bit neatly. So I add this and this together, and what I get in the end is, the union over combinations. Now I'm writing combinations because these different balls, so you have, say, these balls and these three different balls here. So now I need to add this to this, 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 and such combinations. So I'm saying combinations of balls is epsilon xi plus yj, and this holds true. We just go back to the analysis concepts and we can see that the addition of these two would be completely contained within this, and thus I can say that T1 plus T2 is also compact operator. So guys, in the next lemma we see that let X be a norm space and Y be a Banach space. It follows that Kxy is a closed subspace of Lxy and hence a Banach space. Now in order to prove that Kxy is a closed subspace, what I need to do is I need to take a sequence, let's say a convergence sequence, and this is in Kxy, but it's also in Lxy with the limit k. So what I'm saying that this sequence is in Kxy, but the limit is in Lxy, and if I can prove that this limit lies in Kxy, then I can prove that given any sequence, given any convergent sequence, the limit lies in the set itself. So I can thus say that this set is closed. That's how I usually prove that a set is closed. Now what I do is, in order to show that, I choose an epsilon greater than 0 and a number n which belongs to natural numbers such that k minus kn whole norm is less than epsilon by 2. Now why did I do this trick? Well, this is the standard epsilon trick. What you can do is you can always squeeze the difference between your limit and element in the sequence, and you can get this as small as you want. That's the whole point of a convergent sequence. Now since we know that this kn is a compact operator, so kn b10 is relatively compact, makes sense. Now and hence totally bounded. So yeah, we looked at this fact also, that if you are relatively compact, if and only if you are totally bounded, and hence there exist finitely many points knx1 till knxk belonging to knb10 such that this is completely contained in the union of all balls such that the radius is epsilon by 2 centered around knx1. Okay, so now till this part all we have done is use the fact that kn is a compact operator and shown that this fact holds. Now I know from above that norm of k minus kn is less than half epsilon. This I know. So what I can do next is I can introduce this x here. I can say that if this holds, then this holds true, and then what I do is I take an x in p10, then we know that kn of this x must belong to a ball of radius epsilon by 2 upon kn x1. Well, why this? Because before we were taking the whole ball, now I'm just taking one element there, you see, and that's why there's just one ball this time rather than a union of balls. And I also know that for a point x in b10, if kn of x belongs to the ball of radius epsilon by 2 centered around kn x1, and when I look above, if I have kx, then the difference between knx and kx is less than epsilon by 2. So what I can do is say that kx belongs to a ball of radius epsilon by 2 plus epsilon by 2, which is epsilon, and hence I can write this line, and once I write this line I can show that k is a compact operator. How do I show that? Because I show that this is totally bounded. So now we have this corollary which follows as a direct result of this lemma. So in this lemma we saw that the space of all compact linear operators is a subspace, is a closed subspace of the set of all bounded linear operators from x to y. And now all I'm saying is that let x be a norm space, y be a Banach space, and Tn be a convergent sequence of operators with limit with the dimension of the image of Tn less than infinity. Its limit T is compact. So it's a simple consequence of what we did above. We saw that if x is a norm space and y is a Banach space, it follows that kxy is a closed subspace of Lxy. And here I am saying that if Tn is a convergence sequence with the dimension of image of Tn less than infinity, then its limit T is compact.